Welcome back. After learning about the various types of constitutive relationship, now what we shall do that based on that lecture, we shall see some numerical problems about the various types of constitutive relationships which I alluded to in my previous lecture. So, in this lecture, we shall do some numericals. First is the problem on the estimation of gas density. This is a very common problem you have done perhaps also many a times, and you know that we use some kind of gas law, whether ideal gas or non-ideal gas. So, first we take up one problem, that is to estimate the density of oxygen at 90 degrees centigrade and 101.3 kilopascal, that is about 1 atmosphere. And because this pressure is low and the temperature is quite high, high means that how far is it from the critical temperature. So, it is quite higher than the critical temperature of oxygen, and in this case the oxygen can be assumed to be behaving like an ideal gas. So, for this we need to find out the density. So, it is very straightforward, and you can simply go to the ideal gas law, that is the PV equal to nRT, where n is the number of moles. Now, if you rearrange the equation, what you get, that you can take this V on this right hand side and you get n by V. N by V will give you the mole per unit volume, that is the molar density of oxygen. Now, when we talk of density in general, we mean the mass density. That means we need to convert the mole into mass, and the conversion, you know that the number of moles equal to the mass divided by the molecular weight. So, that is what we have done here. So, this density is the mass by volume. So, this n number of moles is the mass divided by the molecular weight, and this we substitute in this equation and we get this particular expression, and from here we can find how to find out the density. So, here we plug in the values of the various constants. Now, whenever you are plugging in the values, I would suggest you that when you are starting, you please write the units of each of the components, because if you falter in putting the right units, you are going to have wrong answers. So, always make it a point initially when you are trying all the problems, you are putting the units of each of the dimensions you are using and check the consistency of the dimensions and the units. So, here we see that pressure we are given in terms of the Pascal, means that means we are multiplying by 1000 to convert kilopascal to Pascal. Okay. And then we have the molecular weight of oxygen as 32 kg per kilomole. Sometimes we also may use 32 gram per gram mole. Okay. Now, here we are reporting everything in terms of the SI units. So, we are putting in this kg per kilomole, and then the universal gas constant, that is 8.314 joule per mole per Kelvin. Okay. Here we are putting in terms of the 8314, that means because we are putting in terms of kilomole. So, we have multiplied the 8.314 into 1000, that is 8314 joule per kilomole per Kelvin. Now, you see, unless we put these units along, initially if you may not be able to understand that why we are taking these values or in what units we are taking the values. Okay. And once you get used to this, then you may not write the units, and this is the temperature in Kelvin. So, once we have ensured that everything is in consistent unit, and perhaps you know that how the joule and Pascal are related. Okay. So, this Pascal is the force and joule is the work. Okay. So, this you know that force into the distance is the work. Okay. So, this that means this joule is basically Pascal meter. Okay. So, this Pascal will get cancelled. Okay. So, this with this now we compute the values and we find that this is the value of the density of oxygen at this 90 degrees centigrade, and the this. Okay. Sorry, this joule is Newton per Newton meter, and Pascal is Newton per meter square. So, Newton per meter square, Newton meter, Newton gets cancelled, and you get meter cube in the denominator, and that is how you get the density as kg per meter cube. Now, we come to the density of the same oxygen at a bit lower temperature, but at a quite high pressure. Now, whenever this pressure is rising so much, we would say that we are no more in the real gas domain, ideal gas domain. It will be the real gas domain now. Okay. Now, whenever we are in real gas domain, we cannot use the ideal equation of state. We have to go for real gas equation of state, and for that we have this particular expression in terms of the compressibility factor. Now, this value of the Z has to be obtained separately, either from some kind of correlations or from some kind of thermodynamic diagram. So, first again what we do, we see that the density is now put in terms of the Z. The additional thing what has happened and which is different from the ideal case is this, the introduction of this Z, and this Z, if it is equal to 1, then we have the ideal gas equation of state. So, here we are going to find out the value of Z, and this Z is a function of the pressure temperature, and we will be showing you one of the ways of finding Z. This is one of the ways from the thermodynamic diagram. Okay. And there are many other ways of finding the Z, and as and when we come to some specific problem, we shall see that what kind of expression or what kind of method we can adapt to determine the value of the Z. So, here you see, to determine the value of Z, we need the reduced pressure, reduced temperature. For that we need to know the critical pressure and critical temperature of oxygen, and here you see the values of this. This is the 5050 kilopascal, and this is about 50 bar. Okay. So, this is the critical pressure and this is the critical temperature of oxygen. Now, in here you find the reduced pressure by dividing the actual value by the critical value. So, here we get the reduced pressure and we get the reduced temperature. Please mind it, the reduced values do not have any units. Okay. Now, based on this reduced value, we shall be now looking into some thermodynamic chart where it gives the compressibility factor in terms of the reduced pressure for different values of the reduced temperature. So, each of the curves belong to different reduced temperature. Now, what you do now, whatever reduced pressure you have found out, you locate it on this x axis, and from there you go vertically up and locate the reduced temperature in this side. So, wherever you find, you may also find that the reduced temperature may not be lying on any of these curves, it might be somewhere in between. So, you have to have proper knowledge of the interpolation methods, so that you can locate the value of the TR in this thing. Once you can locate TR and you find the intersection point and you make an horizontal and read from this y axis the value of the Z. Okay. And here you see the value of Z is coming out about 0.97. This 0.97 indicates it is very near to the value 1, and 1 is for the ideal gas. So, it shows that at this particular temperature pressure there is not a very big difference from the ideality, and that is happening because of the temperature, not because of pressure. Pressure is tending to make it non-ideal, but temperature is also quite high with respect to the critical temperature. Okay. So, that is why you find that the value of the Z is not too much away from unity. So, the gas is almost like an ideal gas. Okay. But if you put this now value of the Z in this expression, you get the value of the density. So, you can see that how much will be the difference if you do consider Z or if you do not consider Z. Next we come to another problem to estimate the gas viscosity, and perhaps you know that gas viscosity and liquid viscosity, they depend on the pressure temperature. The variations in the viscosity with temperature is different in case of gases and liquid. For liquids, the viscosity decreases with increase in the temperature, whereas for the gases the viscosity increases with an increase in the temperature. So, these are some very fundamental knowledge you might be having from your high school science. Now, we shall now look into the estimation way of the viscosity. Here in this problem it is given for low pressure and 125 degrees centigrade. Now, what is low pressure? Generally low pressure we take it by thumb rule that it is a pressure between say 1 bar and 5 bar. Okay. And by medium pressure we take between 5 bar and 10 bar, and for high pressure anything beyond, that is above 10 bar, is taken to be high pressure. So, it is low pressure system. So, we are not really bothered about the pressure, exact value of the pressure, because you will find that for low pressure or this kind of medium pressure we have some correlations which may be independent of the pressure. Okay. So, that is why the pressure has not been mentioned here. Now, you see this is the case here that we have the an expression for the mu which is not having the pressure directly, but it is having temperature in terms of the reduced temperature and in terms of the actual temperature and the critical temperature, but there is no appearance of the pressure. So, that is why it is unimportant for us to know the pressure as long as we are in the low pressure domain. Okay. And here you find that this particular mu r will be used in this particular expression of mu. Okay. Now, to find this mu r we need the value of mu t and the critical values of pressure, temperature, and in this particular expression we need the value of A star. Okay. Now, all these things can be found out from some property tables, and here we have the critical temperature, pressure, the molecular weight, the value of the A star and the mu t. Okay. And here now we find that if we plug in the values we find this is the mu r value, and once we mu r value we take here we find this is the value of the mu we shall be having, and this mu is coming in terms of micropoise. Now, what is this P stands for poise. Actually, poise this poise is used to find as a unit for viscosity in honor of the great scientist Poiseuille, and perhaps you also know that there is something called Poiseuille flow which we are taught in the fluid mechanics. So, this poise comes from the scientist's name. So, here we find that we are having the viscosity of the gas to be this much micropoise. So, micropoise is very small value, and perhaps you know that one poise in terms of the mass, the time and the length dimension, it is basically gram per centimeter per second. Okay. So, this is the poise. Now, next we come to another problem on the liquid viscosity, and here we have to find out the viscosity of liquid at this particular temperature. In this problem also you see that the pressure does not appear because the viscosity of liquid is not a very strong function of the pressure. So, now when we see this particular expression, here you see that here it is coming in terms of density and temperature. So, you see that for liquids density is important, which was not so in case of the gases at low pressure. Okay. Now, here you see that we have these values of these specific constants from some data source, and this is the density and this is the molecular weight. We simply plug in the values of all these in this expression and we get the values of the liquid viscosity. This is in terms of centipoise. Now, centi and micro, centi means 10 to the power minus 2 and micro means 10 to the power minus 6. So, you can see now if you compare these values of the viscosities for the gas and the liquid, expectedly gases will have much less viscosity than liquid, but also what you find the kind of difference we have. We have about 4 orders of magnitude difference between the liquid viscosity and the gas viscosity, and that is why you find that many times sometimes we ignore the viscosity effect in case of gases. That means, we say that viscosity basically gives some resistance to flow over a surface. Okay. So, the less the viscosity, the less the resistance to flow. Okay. And that we know from the in the fluid mechanics, it is very important, and we know that Reynolds number which gives us the type of the flow, laminar flow, turbulent flow, and there we need viscosity. Now, you can now see that because of the great difference in their values of the viscosity, why the Reynolds number becomes so different, and ultimately the nature of the flow also changes because of this change in the viscosity. Now, next problem is on the estimation of vapor pressure of a liquid. Okay, liquid has vapor pressure and this vapor pressure is a function of temperature. So, if you are given a temperature, you should be able to find out the vapor pressure, and here in this problem we are given that we have to use Antoine equation to find out the vapor pressure of acrylonitrile. Okay. Now, here is the Antoine equation, and here you see this is the vapor pressure and these are the values of A, B, C, and in this thing the temperature is in Kelvin and the vapor pressure is in bar. So, you have to be careful whenever you are using any of the correlations about the units. So, if you are using this unit with the kind of values of this ABC, because the values of ABC will change with the different unit systems. Okay. So, here with this we take from some data source these values of this ABC. Now, we just plug in the values over here with the temperature here and we find this is the logarithmic of the vapor pressure, and to find out the vapor pressure we have to take the exponential and we arrive at this particular value, that is 0.112 bar. Now, 0.112 bar, what does it signify to us? It signifies that you know that atmospheric pressure is 1 bar, okay, and this is 0.112 bar. It is much less than the atmospheric. That means, it is not a very highly volatile liquid. The more the vapor pressure, it will go means that it is the more volatile liquid. So, that is what we get indicate from these values of the vapor pressure, and you can also check that if you find the vapor pressure of different types of liquid at same temperature, okay, and if you just compare them, you can see that whichever liquid has more volatility will have more vapor pressure value. Okay. So, this homework you can also try out. Next, we come to another important parameter, that is the diffusion coefficient, and this is used in estimating the rate of mass transfer. For example, you are having some sugar which you want to dissolve in say milk or water. Now, in this case what you will find, if you do not disturb the system, if you simply put the sugar in the water or the milk, you will find that it will take some time to get dissolved, and this rate of dissolution will be dictated by this diffusion coefficient. Okay. So, this kind of system is also there for any other systems like liquid system or liquid vapor system. So, whenever you are not disturbing the system, you are keeping the system undisturbed. So, the mass transfer or the distribution of a component in another component will be occurring purely due to diffusion, and whenever it is diffusion, you need diffusion coefficient or diffusivity, and this diffusivity is a function of both temperature and pressure. Okay. So, it is important for us to mention the temperature and the pressure. Okay. So, this is for allyl chloride in air. So, you have to know which are the two components we are talking about. It is because diffusion cannot happen alone, it has to be between at least a pair of components. So, these are the two components for which you have to find out the diffusion coefficient. So, here is one particular expression to estimate the diffusivity. These A and B represent two components. Okay. And here you see that how it varies with temperature, it varies temperature to the power 1.75, that means it is not linear, it is more than linear. Okay. And with pressure it is inversely proportional to the pressure, whereas with the molecular weight, this also a function of molecular weight, because the heavier the molecule, the more effort it will take to diffuse. So, low will be its diffusivity coefficient. Okay. So, you see that it is inversely proportional to the square root of the molecular weight, and these two expressions, these things are representing the molecular volume. Okay. And you can see that it is also inversely proportional to 2/3 of the molecular volume. Okay. Molecular volume raised to 2/3. So, all these values of these two things will be found in some data source, and this value of the MAB can be found out by taking some average, and this average is 1 by MA by 1 by MAB equal to 1 by MA plus 1 by MB. Okay. So, that is how you find the value of the MAB. Next, we shall take another problem. Here we are going to estimate the density of oxygen again, but now at some different temperature pressure. Now you see the temperature has been reduced to 10 degrees centigrade, but which is still above the critical temperature of oxygen, and this is the pressure, and this pressure is much above the critical pressure of oxygen. So we expect a bit of non-ideality, and let us see that how this non-ideality can be taken into account. Now I have taught you in the theoretical class that there are many ways of accounting for the non-ideality. We can use the various types of equation of state like van der Waals equation of state or virial equation of state. Another approach is to find out the compressibility factor Z. So in this particular problem, we shall be adopting this particular approach of Z, and we have to find out the value of Z from some thermodynamic chart. To find out the value of Z, what we need the value of the reduced pressure and reduced temperature, and to find out this reduced pressure, reduced temperature, we need the critical pressure and critical temperature. So here you see that we calculate the reduced pressure and the reduced temperature by taking the ratio of the actual pressure and the critical pressure, actual temperature and the critical temperature, and these are the two values we arrive at. Now, with the help of this compressibility chart, what we try to do is this, that in this chart on the y axis the value of Z is given, on the x axis the reduced pressure is plotted, and on these various curves correspond to various reduced temperatures. So we first locate the reduced pressure on the x axis and then move vertically up, and then we try to locate the reduced temperature. To locate this reduced temperature point, please understand that you may have to interpolate between two curves. So you need to know the interpolation formula. Once you can interpolate it, then you can find out the intersection of the TR and PR, and from this point of intersection we have to simply go horizontally to the left hand side to locate the value of the Z, which is coming out to 0.97. Now this 0.97 is very near to the value of unity, and that is what that means that this gas is behaving almost like an ideal gas. Now after knowing the value of Z, we plug in the values over in this particular formula, and we find out this is M. So we plug in the values and we find this is the density of the oxygen gas at the given temperature and pressure. Okay. So it is quite a straightforward, and what we have learned that how to look into the thermodynamic chart to find out the compressibility factor. Next we come to a problem to estimate the viscosity. Now in this case we are going for the gas viscosity, and the gas is ethyl acetate, and perhaps you know the formula is C2H5 COOCH3, and this is in vapor state, and the temperature is at 125 degrees centigrade, and the pressure has not been mentioned, it is a low pressure. And you see that the viscosity correlations are given for various types of pressure ranges, and what we understand by low is this: if the pressure is between 1 atmosphere and 5 atmosphere, we take it to be low pressure region. If the pressure is between 5 atmosphere and about 10 atmosphere, we take it to be moderate pressure, and then more than 10 atmosphere is taken to be high pressure. So here, and accordingly where we are in these three pressure zones, the correlations may differ. So in this particular case, you have been asked to find out the viscosity at low pressure zone, and you will find that the value of the pressure is not necessary to compute the viscosity. That is why the pressure value has not been mentioned in this particular problem. Now going to the solution, first we see that we have to find from the appropriate source data, and I have given you the names of the books from which we have collected these correlations. You find that this is one correlation for the viscosity, and this correlation was proposed by Reichenberg. So, we are using this correlation to find out the viscosity of the gas, and here you see that in this correlation we need the value of the critical temperature. The reduced temperature has to be calculated based on the critical temperature and the actual temperature, and then we have two parameters mu r and mu t. Mu r is the reduced dipole moment and mu t is the dipole moment in device, and m is the molecular weight which is coming here, and the correlation says that the viscosity we obtain will be in micropoise. Okay. So, you have to, and here the temperatures have to be in Kelvin. Okay, and pressures, if is there, it is there, it is the pressure is in bar. Now, we look into the property tables from those sources and we get all these values for the particular component. And now, it is now a simple job. Once you find these values, you simply plug in the values in these particular equations and you will get the values of the mu r and the value of the T r. Please note, mu r and T r do not have any units. Now, what you do, you simply put these values of mu r and T r in the correlation of viscosity and you obtain the viscosity value like 99.4 micropoise. Now, please see this 1 poise is 1 gram per centimeter per second, and the poise is an abbreviation of Poiseuille, the famous scientist. So, this is how we are able to find out the viscosity of a fluid. Now, we come to another problem. In this case, it is a liquid viscosity, and here which is the liquid is N-butyl alcohol, and this N shows this is a straight chain. So, the straight chain alcohol, this is the formula, and the viscosity has to be found out at 120 degree centigrade. Now, here you see that at low temperatures for organic liquids, this particular formula or the correlation has been proposed by Auric and Erbar. Now, you see that these conditions have to be very clearly noted, because unless you are noting the particular conditions under which a particular correlation is valid, you again will end up with wrong results. So, whenever you are using any correlation, please make sure the validity of the particular correlation in terms of temperature, pressure and other parameters. So, here the viscosity will be obtained in centipoise, and the rho is the density of the particular liquid at 20 degree centigrade in gram per centimeter cube, and the temperature is in Kelvin. So, with this, now we again get these values of the various parameters from the source book, and we find that as per this Tc and the given temperature, that is 120 degree centigrade, we are getting the value of Tr like this. Now, please note that whenever you are finding the value of the reduced temperature, always convert the centigrade into Kelvin. Okay? Otherwise, you are again going to land up with wrong result. So, you convert it to the Kelvin 393 K and then divide by the critical temperature. Once you obtain the Tr value, you get the values of A, B from again the source book, and the rho is also given there, and this is the molecular weight, and plug in the values in this particular correlation A, B, rho, m, mu, and now you are able to get the value of mu in centipoise. So, you can see that at least that this is coming in centipoise, and for the vapor it was coming in micropoise. Even though the two compounds are different, but the order of magnitude of the viscosities almost remains similar in case of vapor and in case of liquid, and we find that the viscosity of liquid is much higher, about 3 order of magnitude higher than the viscosity of the gas. So, what it means? It means that whenever there is a flow, the liquid will experience more resistance due to drag on a particular surface than a gas. Okay? And this drag force decides the type of the flow we have, like whether it will be laminar or whether it will be turbulent, that will depend on this viscosity value. Next, we come to another important parameter, that is the vapor pressure of a liquid, and you know that vapor pressure decides that how easy or difficult will it be for a liquid to vaporize. Okay. So, here we have a liquid that is acrylonitrile with this is the formula, and for which we have to find out the vapor pressure at this particular temperature, and you know that vapor pressure is a function of temperature. So, we have been asked to use the Antoine equation, and in the lecture we saw the form of the Antoine equation. So, this is the form of Antoine equation, and here what we have to do is this: we have to find out the value of this A, B, C corresponding to the given liquid from the literature. Now, here it has been mentioned that T should be in Kelvin and P sat will be in bar, and this P0 is some reference pressure, and that is 1 bar. So, from the property tables you obtain these A, B, C values and plug in the values in this particular formula, and you get the P sat value as this. That means, you see that the vapor pressure is much lower than the atmospheric pressure, that is 1 bar. What it signifies? It tells us that because it has such a low vapor pressure, so this particular liquid will have very low tendency to go to the vapor phase, and especially under the atmospheric condition, even at that temperature, you find that it is not going to evaporate much, or it will be evaporating very slowly. Next, we come to another important problem, that is the diffusion coefficient, and you know diffusion coefficient tells us that how a particular molecule will be able to distribute itself in another type of molecule. So, here we are asked to find out the diffusion coefficient of allyl chloride in air, okay, at this particular temperature and pressure, and this is the formula of allyl chloride. Here you see there are 3 methyl group and 1 chlorine group. Now, for the low pressure zone, this Fuller-Schettler-Giddings proposed this particular correlation for binary diffusivity, means for 2 component system, this is the diffusivity, and here you can see that it is this diffusivity, this DAB is varying with the temperature raised to 1.75, that is not linearly, more than linear, and with pressure as inverse of pressure and square root of some average molecular weight. Here in this case, A and B represent the 2 different species, and in this correlation DAB will be in centimeter square per second, T will be in Kelvin, P will be in bar, and this sigma V is the atomic diffusion volume. So, now again from the property table, what we do that we can get this value of this sigma V for air and for allyl chloride, and we find the value of the MAB from this particular formula, and then the job is now simple, that you simply put the values in this particular correlation and compute the diffusivity, and this is coming out to be 0.095 centimeter square per second. Now, this is for this allyl chloride into air. Now, you see this diffusivity value will be differing for different types of systems. Now, gases will have the highest diffusivity, then liquid, and least will be the solid. So, depending on the type of the species and its phase, the diffusivity value will keep changing. Next, we come to another important property, that is thermal conductivity. In this, we have to find out the thermal conductivity of copper at 100 degree centigrade. Now, please understand that thermal conductivity is again dependent on the pressure and temperature, not so much on pressure for the solids, but temperature, yes, it is, and so we need to know the particular correlation to find out the thermal conductivity. Now, what happens is these correlations are again based on some kind of experimental data. So, first we shall see that how this correlation is giving the value, and here is one reference we have taken to obtain the correlation for thermal conductivity. So, this is the correlation for thermal conductivity, and this you can see that it is not particularly polynomial, but it has some logarithmic term in this, and in this the conductivity will be in watt per meter per Kelvin and the T has to be in Kelvin. Now, what we do again from that particular reference given to you, you can find the value of this A, B, C, D and then you plug in the values of A, B, C, D here and temperature, you get the value of the conductivity like this 393, about 394 watt per meter per Kelvin. Now, to check that whether this value is right or not or how good is this estimation, what we can do is this, we can look into the actual experimental data of this thermal conductivity and here we have this particular chart given in this particular source. So, from this chart you can again figure out the thermal conductivity of copper as a function of temperature and I have shown you here how to locate the thermal conductivity for the given conditions in this problem and here you can read out the values of thermal conductivity by locating the temperature and you can see that this value is coming nearly same of the value we have computed from the given correlation. So, in this lecture we have seen that how to estimate the various types of properties of vapor, liquid and solid which come under the constitutive relationships. More such properties are there as and when we encounter them we shall see how to estimate those properties. Thank you.